Okay, welcome back. So our next talk will be given by Peter Cimermancic. And Peter, he received his bachelor's degree in biochemistry at the University of Ljubljana in Slovenia in 2009. After that, he went to the University of California, San Francisco, and he received his PhD in biomedical informatics in 2014. During his research, he developed, for example, computational methods for scoring protein-protein interactions, an algorithm for predicting the location of genomic loci, an algorithm for predicting the location of small molecule binding sites. Moreover, he has adopted integrative modeling platform to use genetic observations for determining the structure of molecular assemblies. And currently, he's a scientist working at Verily Life Sciences, and he's applying machine learning to life sciences and health-related challenges. So his talk today has the title High-Quality Peptide MS Spectrum Prediction Using Deep Learning and Its Application to DIA Data Analysis. So welcome, Peter.
Thank you. Okay. Hi, everyone. Good morning. Where's the person who suggested me yesterday to have lots of beers and sangria? I listened to you, and thank you. Now I feel not so good. Anyway, it's a great pleasure to be here. Thank you to the organizers. And to be honest, I'm relatively new to the mass spec, so I'm learning a great bunch, and thank you to all the presenters. So today I would like to present work that was done by several people from Verily Life Sciences, where I'm from, Google Brain, and Jürgen Koch's group. And just to give you what we're going to go through, so I have an unusual background. I work in industry. I want to give you some background on what do we do, who we are, followed by a quick intro into machine learning. This is a technique approach that we use very often, and then dive deeper into challenges in proteomics and how did we address one of them. So Verily Life Sciences is a relatively new company. We emerged from Google. We were initially part of Google X, or Google Life Sciences. And when Google restructured into Alphabet, we rebranded ourselves as a Verily Life Sciences. We still have pretty strong ties with Google. We have access to the latest and the greatest in machine learning, to their people, and more importantly, to all the perks, including free food, as that was presented many times. Sorry about that. Our mission is to collect health information and make it useful so people can enjoy healthier lives. And we do so by focusing on 4 different areas. We have projects spanning precision medicine. These projects include clinical studies, including those that are focused on cardiovascular diseases, Parkinson's, multiple sclerosis. And we also develop new platforms, for example, Immunoscape, that's used to profile immune system. We're also developing a lot of sensors, as you can see over here. This is a smart contact lens that is meant to use to measure glucose levels. The same for this patch. Study Watch can track your activity levels, heart rates, and ECG continuously. We also do a lot of projects that try to intervene with diseases. Debug is actually my favorite one. That one is meant to eradicate mosquito-borne diseases such as Zika or malaria. And definitely go online and check more about it. It's a really cool one. And then finally, the 4th, let's say, umbrella of projects that we are working on are related to health platforms. For example, the one that's the furthest along is on Duo. Here we are building a platform that is trying to manage life of people suffering from diabetes. But I wanted to focus just for a little bit on the project baseline, just because I think it's the most relevant for the audience here. So the goal of this project is to map human health. Some of the questions that we would like to answer include, what does make us healthy? Or can we detect diseases early on? And the motivation behind this project is here. So we have cars that have many, many different sensors. For example, we can measure speed, we can measure oil levels, gas levels, tire pressure, and so on. All of these sensors in aggregate collect 1 megabyte of data per second, so quite a bit. But when we look at our own bodies, there is not much that we measure there. Most of what people do is they will step on a scale, measure their weight every now and then, and I get surprised every time I do it, but that's about 12 bits of data per day. As you can see, there's a huge discrepancy between the data that we measure on something as simple as cars and health data that we collect on ourselves. And I think we can all agree that having all of those sensors in cars makes us maintain the car better, which in turn increases longevity or how long the cars last. And if we did the same for our bodies, we could probably live healthier, longer, and so on. At least that's the idea. So how do we do it? We have launched this project Baseline about a year ago. We've recruited thousands of participants, and we just measure anything we can possibly measure on them. That includes going through their medical history, medical records, imaging from X-ray, CT scans, and so on. They are wearing a bunch of different sensors, including the study watch that I mentioned. And most importantly, we also go through molecular labs. So we just measure all the omics in different bodily fluids. And the omics includes metabolomics and proteomics, which is to the interest of here. But the goal of this study is not only to collect this data, it is also to analyze it with the best possible tools available. And in some cases, the tools are not sufficient, so we are going to develop our own tools or improve on the existing one. And since we are part of Google/Alphabet, how do we do that? Machine learning. Quick intro into machine learning. So the type of machine learning that we use most often is called supervised machine learning. That means that we are building models that are trying to map certain input to a certain output. For example, we can take a photography of a cat and have a model trying to predict what's on that photo, cat. We can have a model that's going to take as an input an email and try to predict whether it's a real or a fake or a spam. We can have a model that's going to take an audio recording and try to transcribe it into text or language translation and so on. The exciting thing about machine learning these days is that they have started to outperform humans in many different tasks that we thought it's not going to be possible just a few years ago. For example, image recognition. So for example, detecting whether there's a cat on a photo or a dog on a photo. You can see that just a few years ago, the most recent algorithms started to surpass humans in terms of accuracy. And this is not only detecting cats and dogs in photos, this is actually trying to classify over 10,000 different categories. What made it all possible? Deep learning. And deep learning are just modern reincarnation of neural networks. The new advantages that made all of this accuracy and performance possible are new architectures that we have come up with. So the neural networks now are very deep, they're very complicated, complex, have complex architectures and so on. We, not just Google, but in general, we have developed new math that allows training of these large neural networks. And there have been many advancements being made, both on the hardware side and on the software side. What you can see here is a processor called TPU. So you're probably all familiar with GPUs and CPUs that you have in your laptops. Well, we have built our own processor called Tensor Processing Unit that's specifically designed to do machine learning and machine learning only. We are also developing our own language or infrastructure, library, computer library, to do machine learning at a very large scale. And yeah, right now, machine learning is integrated in pretty much every single product that Google offers, from Photos, Inbox, Maps, and so on. And we also have many projects related to biology or life sciences. And just to give you three quick examples, the first one is related to predicting or diagnosing diabetic retinopathy. Diabetic retinopathy, it's a major cause of blindness, especially in developing countries, and detecting it as early as possible is going to help people see longer. The algorithm that the team at Verily and Google Brain has put together, you can see performs on par with human experts, and it's already being launched in several countries, including India. Second project includes tumor detection in pathology images. And you can see here that also computers started to overpass accuracy of human experts, not only in accuracy, but also in time. For example, it's going to take pathologists over 1 hour to go through this image, whereas computer can just do it in a blink of an eye. And then the third example is from the genomics field. We have developed an algorithm that is really good at variant calling from next-gen sequencing data. The algorithm is called deep variant, and it's getting more and more popular. And as many other tools, it's much better than anything else on the market. We have also identified lots of opportunities for machine learning in proteomics. And the reason for that is that there is just lots of data out there that's available. For example, Pride database has tons of data that we could use for training. And second, when we look at trends, there is not many people who work on computational proteomics yet. For example, if you look at Google Trends for 2 terms, computational genomics, computational proteomics, you can see that computational genomics has quite a lot of interest over time. But the audience over here, it's probably a big portion of people who are interested in computational proteomics. And I take that as a huge opportunity. Like, we can all develop something new and make computational proteomics very interesting. Second score that we usually look at to see how popular a field is the FC score, or funny cartoon score. So if you just search Google Images for funny cartoons related to computational genomics, you're going to find tons of funny cartoons. If you do the same for computational proteomics, the funniest one that I could find was this copy-paste. I don't know, I don't find it funny, but okay. So yeah, to get more serious, 3 largest challenges in computational proteomics are: 1, identification rate. So if you look at any given data set in proteomics, right now we are only able to identify or annotate, let's say, 25% of features in mass spectrum. Second one is quantification, and here I'm referring to label-free quantification. There is lots of work that needs to be done on that end as well. And then finally, the field is quite divided by using different formats, different analysis tools that are not compatible with each other, so we could improve there as well. The project that I'm going to discuss next is trying to push the limits on the identification part. We call it DeepMass Prism, and we primarily designed it to use it for analyzing DIA data. This is what we use in-house most of the time. Just very quick recap. In DIA data, we split our sample into 2 parts. We use the first part to collect data in DIA mode. DIA mode collects MS spectra that are actually a mixture of MS spectra from multiple different peptides, which are hard to interpret. And that's why we use the second half of the sample to collect spectra in DDA mode, and we use that to build up spectral libraries that are then used to interpret DIA data. As you can see, this process or this approach is not very efficient. We have to run two pipelines basically in parallel. And the number of proteins that we can see with this approach is limited by the number of proteins that we get by DDA data. And that, as we know, is very sparse and requires quite a lot of work to get more complete coverage. What we would like to change here, or the change that we are proposing to make, is basically to get rid of the second step. We would like to replace spectral library building by DDA with spectral library building by computers. So we would like to develop an algorithm that's going to build spectral libraries. At least that's the idea. And ideally, if all goes well, we would like to improve the efficiency both in time and cost, because we don't have to we don't have to go to the second workflow. And because we can build computers, or because we could build spectral libraries by computers, we can just keep adding peptides to it, which hopefully in turn will increase the number of proteins that we see in our samples. So to summarize, what we would like to achieve is to build a supervised machine learning model that's going to take a peptide sequence as an input and output its MS spectrum. As mentioned yesterday by Fabio, there are already tools on the market that can do that. They are using conventional machine learning models, and those have many different limitations. One is they cannot work with variable length inputs. Peptides, they can come with different lengths, and state-of-the-art tool, MS2Pip, had to develop one model for each different length of a peptide. That means losing information because you have limited amount of information to train one model. You are splitting your data. Second limitation is that they can only predict one type of output. For example, they can only predict Y ion intensity or B ion intensity, but there is quite a lot of information if you're trying to predict both of them at the same time. So they're losing information there as well. Third, they cannot, or let's say with standard approaches, conventional approaches, it's difficult to incorporate metadata such as fragmentation type, mass analyzers. The way earlier approaches solved that was to, again, build multiple models, each one for different fragmentation type, mass analyzers, and so on. And finally, conventional approaches are difficult to train at a large scale. So if you have lots of data available, those are going to have really hard time going through that, which again means losing information, precious information. So all of these disadvantages, let's say, result into suboptimal performance. For example, MS2-PIP, if you look at the correlation between predicted and measured experimental spectra, it's going to be about 0.85. We would like to improve that. So collaborating with the Cox group, we have collected lots of data from the Pride, annotated it using MaxQuant. The number of data sets that we've looked at was 25 from 5 different organisms that resulted in about 1.5 million unique peptides or 60 million PSMs. Here are just some basic statistics on the peptides included in our data set. You can see we have many different charges, 2 different fragmentation types, peptides come in different lengths, and we use 2 different mass analyzer types. And this here is schematic for the model that we put together trying to tackle this problem. The model can be split into 2 modules. The first module, RNN, neural net, is used to encode peptide sequence that, again, is a variable length input into a fixed length representation of that peptide, and that would be located somewhere here. Once we have that, we can combine, let's say, this fixed length representation of a peptide with any type of metadata. In our case, metadata included peptide length, charge, mass analyzer type, and fragmentation type. So we can put these 2 together and then send all of it through the second module, fully connected layers. These are also neural nets that can finally emit different types of information. In our case, we've predicted intensities of Y, B ions. We also have a model that can do different neutral losses or B ion types at multiple different charges. And the nice thing here is that all we need is one model to take all of the data in. Doesn't really matter what fragmentation type, mass analyzer did you use, what peptide length did you use. All of it can be modeled in one single model. So we've trained the model. It takes about 2-3 days on GPUs. GPUs, in this case, were about 30 times faster than CPUs. And here is just one below average example of the prediction for this peptide. So this is an experimental MS spectrum, and this is the predicted one for Y and B ions only. And the correlation here is relatively high. It's about 0.9. When we look at, so we've split our training data, our data set that we had available into training, testing data set. When we evaluate cross-correlation on all of the peptides, there was about 60,000 of them from our testing set. This is the result that we obtained. DeepMass, as we call algorithm, our algorithm has cross-correlation, median cross-correlation of about 0.95, which is significant improvement over MS2-PIP with cross-correlation score of about 0.87. And the 95 comes actually pretty close to the technical variation defined as technical reproducibility. This is a theoretical upper bound, let's say, defined as taking one peptide and measuring its spectrum twice. And the nice thing here is that the model performs very accurately across any data slice. So for example, if you look at different charges, you can see that it's doing very well. The same for lengths, mass analyzers, and fragmentation types. And this, again, is all one single model, whereas in the case of MS2-PIP, each box would be a different model. Okay, so this was the accuracy. What we wanted to do next was to look into how well or why does the model work so well. The first thing that we looked at was to check fragmentation efficiencies between pairs of residues. This is a result from a published study where they looked into a data set, many published data sets, and looked at fragmentation efficiencies between a couple of residues, both for B ions, Y ions, CID fragmentation, and HCD fragmentation. And we can do the same with our model just by computer. We looked at this template. I apologize for formatting getting destroyed by converting to PowerPoint. But yeah, we use this peptide template and look at fragmentation efficiency between X and Y position, and then constructed these sort of heat maps as well. I apologize for the color map not being the same, but if you look closely, you will see that they are highly, highly similar. And the nice thing is that by computer, we can start filling gap for the data that didn't exist in reality. So that was one really nice confirmation that our model does what it's supposed to do. Next, one question that we were very interested answering was how much, so if you look at intensity or fragmentation efficiency at one position, how much do positions that are pretty far down or upstream the peptide sequence matter for that fragmentation efficiency? The way we decided to measure that was to do some sort of interpretation of our model. That's pretty difficult to do with black boxes, but there are new approaches out there, including integrated gradients that's used to measure something that's called attribution. So going to the image classification case, using integrated gradients, we can highlight pixels from the original image that the model used to make a call. For example, here are the pixels the model focused on to figure out that this is a camera on the photo. The same for mosque, bridge, and butterfly, and so on. So we can apply this model to, we can apply this approach to our model as well. And what you would get out is basically so if you focus again on one position in a peptide, you would get out importances of any other positions in peptide sequence. And those importances or attributions can be both negative, so there can be positions that can suppress the intensity, peak intensity at a given position, and there are going to be positions up and downstream the peptide sequence again that will increase, let's say, fragmentation efficiencies. So we have first run that on one single peptide example with this sequence. And you see here the attribution heat map for both Y and B ions. So let's say, just as an example, if you focus on glycine over here, you can see how the fragmentation efficiency or peak intensity at that position is being affected by all other residues within that peptide sequence. And the blue here is a positive attribution, meaning that they increase peptide fragmentation. And the red one is negative attribution, meaning that they decrease fragmentation efficiency. I know this is pretty hard to read, but it looks pretty interesting. Diagonal, for example, does make a lot of sense. So there is a lot of importance of the residues that are right next to the fragmentation side that we are interested in. That's why we have pretty strong signal on the diagonal. But you can also see a lot of either blue or red cells that are highly intense further away from diagonal, meaning that there are some long-range interactions needed to be able to, that influence fragmentation at any given site. Again, I wouldn't want to make too many conclusions based on a single peptide, so we ran these for a subset of 1,000 peptides in our data set, and here are distributions of these attributions. So and these are normalized distances away from the fragmentation site of interest. So what you can see here is that for Y ions, what matters the most is actually the distance from the fragmentation site. That makes sense. And that's true both for positive and negative attributions. But when you look at B ions, what you see there is that the most important information is coming from the downstream of the fragmentation site, and that positively influences fragmentation point for B ions as well. And there's almost nothing on the upstream side of the peptide sequence. So using this type of deep learning, this type of approaches for interpreting deep learning, we can learn something new about the chemistry of fragmentation as well. I'm just checking how much time do I have left. Okay, so that was interpretation of the model. Next, we wanted to apply it to the DIA data processing. We have collected DIA data for healthy individuals, plasma from four healthy individuals, and then constructed spectral libraries in 3 different ways. One, by using DDA, second one using our model, and the third one as a control using our model, but we reshuffle the intensities. What you see here is the number of peptides identified by using different approach. And as you can see, one important thing that I missed, the spectral library with DeepMass was constructed for exactly the same peptide that we identified with DDA. So we didn't try to increase the spectral library size automatically yet. So what you can see here is that the number of peptides identified is almost exactly the same by using DDA or DeepMass approach to build spectral libraries. There are a few that we missed. There was about 80 of those out of 5,000 something that we missed. And those, as you can see here, had really low Q values or high Q values to begin with, meaning that they were not that significant to begin with. When we look at the quantification ability, again, we see really high correlation between intensities that we obtain with spectral libraries using DeepMass and DDA. So this all suggests that we can replace spectral library building by DDA with a computer. Another check that we have done, so I mentioned at the beginning that we have many clinical studies going on. So we looked into one of those. It involves a disease that we are interested in. We have a list of known biomarkers from literature, about 300 of those biomarkers that we wanted to see in the data set. By using DDA spectral library, we will only able to see 60 out of 300 proteins. That's about 20% of those. So what we decided to do was to expand spectral library using DeepMass for all of the missing proteins, and then just reran the analysis, and this is what happened. So using DeepMass, we can now start seeing many, many, many more proteins. So in this case, we've increased the data set, the number of proteins that we see, by over 35%, which was, I think, pretty cool result. So that's pretty much it. In conclusion, again, we demonstrate that we are able to build spectral libraries with high accuracy using deep learning. We can use the newest, let's say, approaches for interpretation of these models to be able to get something new out of the data. We can maybe even learn something new about the chemistry. And finally, we can successfully apply this approach to analyze DIA data. And finally, I would just like to acknowledge all the people involved in this project, COGS group that's here, my colleagues at Verily and Google Brain. And if you are interested in giving this tool a try, you can join this Google group or read more about how to use it at this URL. I warn you, it's not gonna have a graphical interface. It's gonna run through command line, but hopefully that's not gonna be too difficult. Do we have time for one last thing? Okay. Okay. So DeepMass is actually just, or DeepMass Prism, as we call it, is just one of the projects that we would like to build in the proteomics field. We would also like to focus on de novo sequencing, quantification, biomarker prediction, and in fact, if we had more and more, once we have lots of data available, we could build a single model that would go end to end. So we actually started working on DeepMass de novo already, with the goal being just the reverse of the DeepMass Prism. So now we would like to go from spectrum back to the peptide sequence. We haven't really invested much time into that. All we have done so far was to use Google Translate code. It's another machine learning tool where we're just going to replace one language with spectrum, MS spectrum, and hopefully we'll, instead of getting a different language, we'll get a sequence of amino acids. So we have done that on the same data set pretty much. And this is the performance that we get as compared to the PEAKS. That's the most widely used tool for de novo sequencing from mass spec data. So you can see we can perform quite well. We are about 15 to 20% better than PEAKS, but there are still a lot of improvements that we could make. Again, this was just Google Translate code pretty much out of the box, and we are doing pretty well already. And that's pretty much it. Thank you, everyone, for listening.
Thank you, Peter. Very nice talk. I'm pretty sure we have many questions.
Hi, thanks for the nice talk. One thing you didn't go into detail with were retention times. Do you also predict retention times, and how did you use them in the data you showed?
That's a good question. So in this work, we haven't predicted retention times yet. We are working on a model that's going to do that. But in principle, they could be included to the same model. We don't even need a separate model. We could just include the retention times as another type of output that the model predicts. And retention times are not that difficult to predict. We have tried that with simplistic stuff. It can work very well, especially for the IA data set where a lot of people just include IRT peptides in it, so we get normalized retention time as opposed to seeing all the variances that different columns, different labs would produce. So we can predict standardized retention time quite successfully.
So in your benchmark, you basically also ran the DDA database matching without using the retention times from that library, or did you include
No, we borrowed retention times from the original DDA library in that case.
Okay, and so did I see that right, that the control bar was basically the false positives hits, and that was 60%? Or
control bar?
So there was a red control bar, and you said those were random sequences for matching. And does that mean 60% FDR?
No. So what that means is that, so when you look at peak intensities for a given peptide, what you will see that they follow some sort of a logarithmic distribution. So you have a few peaks that have high intensity and many peaks that have relatively low intensities. So what happens when you reshuffle these peak intensities is that intensity for most of the peaks is not going to change. So that's not going to affect the results that much, which is why we are still seeing quite high peptide identification rate. Does that make sense?
Yeah, it does. Yeah, yep. I understood that wrong. Thanks a lot.
Sure. Yeah?
Great talk. Really nice work. So I was wondering whether if you compare it to direct DIA or have thought about integrating it into your model, maybe this could get even better, right?
By direct DIA, you're referring to the tool that Biognosys offers, Spectronaut, or?
No, so direct DIA in compared to DeepMass.
We
so
haven't,
in terms of the number of identifications, if that...
well, we have, well, you probably, by direct DIA, you mean the tool that's within Spectronaut? Because they have to. Okay. So we have compared that. The direct DIA usually doesn't perform that well. You will see about half of the peptides, the number of the peptides that you would see with DDA spectral libraries. So in our case, we can do much better than that. And actually, so as I mentioned at the beginning, we can increase spectral libraries pretty much indefinitely, and we are using it to learn more about proteogenomics and stuff like that, like variants. We can track those as well, or different organisms present in different bodily fluids and stuff like that. So I'm very confident that we can do much better than direct DIA, and we are seeing some preliminary data that supports that.
Okay. And the second question is, so when you make the intensity predictions for your MS spectra, do you also, or can you also predict how that correlates to the MS1 intensities and sort of, because I'm kind of trying to think that you could then sort of combine it with boxcar kind of an approach.
So we've been thinking about that. So right now, all of the MS spectra are being normalized. We are not really taking their absolute intensities into account within a data set, but I think that would be very useful information to have too. What that would allow you to do is to add another type of an output that could be just intensity of that peptide. So yeah, that's a good point.
Fragmentation efficiency or something like this.
Okay, other questions?
There was one question over here.
No, there wasn't.
Just wondering if you are dealing also with post-translational modifications and how successful you are with that.
Yes. So what we have right now is version 1. In the subsequent versions, we would like to include PTMs as well. I think the phosphorylation is one of the most famous one that people use, so we would like to add that one. It's just a matter of having data sets available for something like that, and then we can easily add those, no problems, to the same model. Again, it would be one model that can deal with all of this stuff.
But not unbiased, for example, like You don't have a way to do something like dependent peptides or unbiased identification of, like merge it with your de novo or something. So in your de novo kind of include also potential PTMs.
So yeah, for de novo model, what matters the most is just the alphabet size. In the case of amino acids, that's 20, or we do include some PTMs already, like oxidation of methionine and so on, or cysteine, carbamylation of cysteine. We include that already, and we can arbitrarily increase that alphabet for other PTMs as well. And as long as we have data available to build the model for the other characters in the alphabet, we can do so easily for anything.
Oh, one question.
Very short one is TMT or isobaric labels. Are they also in the pipeline?
Not yet, but we can add them to it. There's lots of interest.
Yeah, would be very interesting for us.
Okay, so
Thank
then
you, everyone, again.
Let's thank Peter again for this very nice talk.